Okay, so let's see. Today, what I was going to do, was to discuss just to finish discussing like this stuff about how you can use like the wedge product to. I'm trying to connect this by cable. Just to connect how to use the wedge product to find the gradient, the curl, the divergence, and all these things. Um, and then how do you discretize those on visual complex. Once we have that, then we can discuss, I think probably on Thursday, we should be able to begin talking about that. How is that can be put to use for this like statistical ranking problem. There's also like a fun application to game theory, which I'll mention as well about these ideas, which is kind of like, not necessarily, like super um not something you would expect. So I like when the applications are kind of like unexpected. So that would be a fun one as well. Let me, since it has been a while since I last saw you, let me just remind you what the setup is for the wedge product. So again, what I was mentioning a week and a half ago, I guess, is that the way you should think about the wedge product is kind of like a fixed version of the cross product. So when you have two vectors, right, the cross product was a vector that's perpendicular to the parallelogram that the two vectors make up. The wedge product kind of like takes that out of the picture and just focuses on the parallelogram in itself. So for example, as you can see in this picture, you watch V is supposed to be representing somehow the parallelogram. The thing is that the order matters because depending on which one you write first, then that means that you're moving along the parallelogram either starting with U or starting with V, which in this case, like depending on how you look at it, it means that you're moving either counterclockwise or clockwise. So that is why you still have the situation that U wedge V is minus V wedge U because they have what's called like different orientations. Um, and then the nice thing about the wedge product, the reason is why it ends up being superior to the cross product is that when you do cross products, you always keep getting vectors. So you cross V is a vector, and if you cross that with something else, that's also a vector, and if you cross that with something else, that's also a vector. So you never move away from like getting vectors. Whereas the wedge product, it kind of like keeps increasing the dimensionality of the things that are involved. So for example, if you had like the wedge product of three vectors like UVW, the idea is that you make up the box, like the parallelepiped, which you see there, and then the wedge product is supposed to represent in some way that box. That's kind of like the idea, but it's kind of like in a sense three-dimensional. So when you have a wedge product of two vectors, that is two-dimensional because that's kind of like a parallelogram. And when you have the wedge product of three vectors, then it's kind of like a cube. And if you had four, that would be like a hypercube and so on. But usually, if you kind of like understand well what happens with two and three vectors, like you kind of have a pretty good idea of how things are supposed to look like. And then what I was saying, let me just what you have to really remember of all these things that I was saying from a week and a half ago is that the main properties of the wedge product are kind of like similar to the cross product, where if you switch or swap two of the factors, you get a minus sign, which in particular forces the wedge product, like I should have put here a U. See, so like U wedge U should be the zero parallelogram. So the wedge product of any vector with itself gives you zero, basically, that's the idea. And then you can kind of like distribute as with regular multiplication or regular dot product or regular cross product. Okay, so those are kind of like the basics of how the wedge product is supposed to work. Then what maybe before that, is that okay? Now, okay, now really the fun part, what makes a very interesting construction is that you can kind of like summarize everything that you learned from Calc 3 using the wedge product. It is kind of like a very fun thing to do because then you don't have to memorize anything, which is always nice, not to memorize things. So the idea, and that this is what people goes under the name of like exterior derivatives or differential forms, but I'll just kind of like give you like the concrete way to think about this. So again, just to kind of like relate this to what you do in Calc 3, when you had in Calc 3, what you would when you had a function of one of three variables, like a function of x, y, and z, what you would like to find is the gradient, right? Like the gradient of that function. So the gradient of that function, if you remember, is just like the partial derivative with respect to x in the x direction, the partial derivative with respect to y in the y direction or the j direction, and the partial derivative with respect to z in the z direction or like the unit vector k. So that gradient that is totally fine, right? It's just that here it kind of like gets like this like different name, which is just called df. So like you call it df instead of grad of f, but it is like, the formula itself is literally the same formula. There's something that I have changed and E1, E2, E3, and just using it sort of I, J, and K. But if you look at it, it's exactly the same formula that you know from Calc 3. Um, Now, the thing, what makes this like a bit more interesting is what happens when instead of a function, you had like a vector field. So again, what was a vector field from Calc 3? I'm calling it F, so uppercase F, so you can think of it as kind of like a force field. So a vector field is kind of like a force, right? Like so, it's everywhere in space, but it is allowed to depend on the point in space, kind of like a magnetic field or an electric field, things of that sort. So that's why it's kind of like something in the I direction, something in the J direction, something in the K direction, but those components can be themselves functions of X, Y, and Z. So that's kind of like the more general definition of what a vector field is, which again, in Calc 3, you use that to find the work along a vector field or like, the flux, if you remember those sorts of things. Uh, and so the idea is just as before, now you define what you would call like the exterior derivative of the vector field, okay? And it's just basically, again, like here, like it's kind of like a function times a vector, a function times a vector, a function times a vector. If you look at what the vector field is, it's function vector, function vector, function vector. So the exterior derivative, what it does is just takes like the derivative of each of these functions, which is another way of saying the gradients. So you take the gradients of each of these functions and then you wedge them or like take their wedge product with respect to the corresponding vector that was left. So for example, in this case, it would be the gradient of the first one, wedge the vector E1, plus the gradient of the second one, wedge the vector E2, plus the gradient of the third one, wedge the vector E3. And then what I was working up last time is that if you do this, like, again, what is df1? That is literally just the gradient of f1. So you write the formula for the gradient of f1, you do the same for f2, and then you do the same for f3. Okay? So those are just like the gradients, but now they get wedged with E1, E2, E3. Okay? And then what you do is kind of like a bit of a mess, but you kind of like start like distributing. So you do E1 with wedge E1, E2 wedge E1, E3 wedge E1, and so on for the other six. Okay? Let's see. Oh, okay, yeah, which is kind of what you see here. What I did here is that right. What happens, and this is what I was saying a bit earlier, is that for example, when you do E1 wedge E1, you don't see that one because it's a wedge of a vector with itself. Or here, when you see E2 wedge E2, you also don't see that one. In the same way in which I cross I was 0 or J cross J was 0. So it's kind of like the same idea. And E3 wedge E3 also goes away. So of the 9 possibilities, right, because 3 times 3 is 9, of the 9 possibilities, 3 kind of die off immediately. And that's why on the next page, we only had 6 things left, right? E2 watch E1, E3 watch E1, and the other four possibilities. Okay, so but then the idea is that of these six remaining ones, you can kind of like match them in pairs because, for example, E1 watch E2 and E2 watch E1, they're basically the same thing except for a sign, right? Like they kind of just differ by a sign. So you can kind of like factor this one together um, with a negative sign, and that is what I was, ended up doing towards the end of the final class. Okay, and then you end up with this formula. Okay, which if then you have to think, oh, does that look familiar to anything that I recognize? And then what you have to realize is that, oh, okay, these quantities, these weird combinations of partial derivatives, those were exactly the combinations that you have to take when you're finding the curl of a vector field. So kind of like magically, kind of like the curl like the entries of the curl are kind of being reproduced in this formula. So the exterior derivative of a vector field is more or less the curl. It's not the curl literally because the curl was a vector field, but it's kind of like a divector, like a two-dimensional version of the curl. That's because like again, E1 wedge E2 is kind of like a parallelogram. Same with E1 wedge E3 and E2 wedge E3. So it kind of like produces the same thing as the curl in the sense that it has the same formulas for their components. It's just that now instead of regarding it as a vector field, this thing is being regarded as something kind of like two-dimensional, like kind of like a field of parallelograms of sorts. Um, but they are basically the same formulas as the curl. Does that make sense? So far, so good. Okay, so what I'll do, okay, so let me do this for the last one so that you see that the divergence kind of like comes out in exactly the same way. And then I'll kind of like start discussing how do you find an adequate version of all of these things on a simplicial complex. Again, a simplicial complex, you can think about it like in, like kind of graphs with some triangles or tetrahedra all like interacting with one another. Um, but it's useful to see what I'm the reason why I'm trying to do this is to kind of like convey the fact that in a sense like the correct definition of the curl should have been something kind of like two-dimensional. So the gradient is one-dimensional because it's a vector field. Let me actually put that oops, oh my god, I have so many classes. Let me just copy paste this. So the idea is that what I'm the way to kind of like keep kind of like to have like a mental picture in mind is that you should think of a function f of x, y, z as somehow being like zero-dimensional just because it's kind of like a scalar, and a scalar has like no extension. So like a function is kind of like in a sense zero-dimensional. But then the gradient of a function, right, which you would call df, which is like the gradient of f, right? Like the gradient is supposed to be a vector field, so it's a bunch of vector fields. So because they're vector fields, they're kind of like, in a sense, like one-dimensional because a vector has a length. So that's what the only reason why I mean by one-dimensional. It has units of length. Um, and then if you had, and then if you have a vector, if you have a vector field, right? Again, that is kind of like one-dimensional because it's like a force field, right? That's kind of like a force field, which again, you can think of it as kind of like the electromagnetism. Then is differential is df is exterior derivative, which is how that's called. Um, that is what more or less coincides with the curl, right? So again, this is basically the curl of the vector field, but they put quotes in curl because it's again now being regarded as being two-dimensional. So it is kind of like more of a bunch of like parallelograms in some way. So it's like, it's kind of like a slightly different picture because again, when you have a vector field, you imagine a bunch of arrows in space. So in this version of the curl, you imagine a bunch of kind of like parallelograms rotating in space. So it's kind of like the space is kind of gets filled in with tons of parallelograms. And so that's kind of like two-dimensional. Okay, and then what I want to show you is now just to kind of like practice this exterior derivative stuff is that if you have something that's kind of like two-dimensional, like a bivector field, which is kind of like maybe like the first time you would see that, but if you have, then its derivative would be kind of like three-dimensional, that would be actually the divergence. So that's where like the divergence comes in this picture. I'll call this one B because the magnetic field is actually best regarded as a pseudo vector. I think I told you this like a couple of classes ago. Like the magnetic field is more really like a pseudo vector than a vector. So if you want to, you can rewrite Maxwell's equations using wedge exterior forms or like the wedge product. And then in that, if you do it that way, you think of the electric field as a vector field, and then you would think of the magnetic field as a bivector. So I'll just write it as B for that reason. But the idea is that if you thought about this as a kind of like what a bivector field would be kind of like a bunch of like these oriented parallelograms, which again, this would be two-dimensional. And then its exterior derivative, which is what I'm about to show you, would be kind of like a version of the divergence of this thing. So this would be kind of like the divergence corresponds to what in Calc 3 you would have called the divergence of B. Well, I guess I don't have to put the arrow here because it's not an arrow. I'll put kind of like a parallelogram. I'll draw kind of like a parallelogram as a subscript just to remind you that I'm thinking by vector field means that it's kind of like some sort of parallelogram. So that would be kind of like some sort of like oriented box because it's going to be three-dimensional. So like the only thing that I want you to notice here is that from this perspective, when you take this derivative, the idea is that when you take this exterior derivative, you kind of like what it produces increases the dimensionality of the object by one dimension. So the point is that when the way this is defined, the way this exterior derivative is defined is is so that it increases the dimensionality of the object by one. Which again, like in Calc 3, that was already true with the gradient because again, like if you have a scalar field and if you take its gradient, it's a vector field, and vector fields have length, whereas scalar fields like don't have length because they're just like points. Um, but in Calc 3, like you don't do the rest don't kind of behave that way because like you still want to think of the curl as a vector or the divergence as a scalar. So that's kind of like the main difference. Okay. So let me show you how that works for this bivector field. Um, and again, the nice thing about working on R3 is that you can be super concrete. So on R3, So what we were talking about on our about this like last time is that on R3, you kind of have like three basic parallelograms in the same way in which there are like three basic unit directions, right? Like the x-axis, the y-axis, and the z-axis. The idea is that on R3, there are kind of like three main parallelograms, which are like the ones on the xy plane, the xz plane, and the zy plane. So the one on the xy plane is built out of E1 and E2 because that's the I and J directions. So this is the one that I would call E1 wedge E2. Okay. So that's kind of one of the basic ones. And then the other three, right? The second one is the one that lives kind of like on the YZ plane and is this blue one. So this one would be kind of like, for example, you can write it as E2 wedge E3, okay? Which again is kind of like I wedge K. Okay, and the last one is kind of like the one that lives on the XZ plane or ZX plane, which then this one would be called like E3 wedge E1. Uh, okay, just to use like yeah, I'm just moving cyclically so yeah, like that. I'll just do. Okay, so those are kind of like the three basic parallelograms, and the idea is that any other parallelogram in on R3 in a sense is kind of like a linear combination of these three. And so if you have in the same way in which a vector field, you could write it in terms of I, J, and K. The idea is that by vector field, you would write it in terms of these three unit parallelograms. So these are kind of like the analogs of I, J, and K in the world of parallelograms. Okay, so these three are the analogs of I, J, and K in the world of parallelograms. Okay. So you can write the bivector field. If you had a bivector field, you would write it as okay. So here is where you do have to be a little bit more clever, and you'll see what I mean by that in a moment. Uh, just so that it looks very closer to what the formula for the divergence is. So the thing is like any by vector field would be kind of like a linear combination of these three things, right? So basically, it has to be something times the first parallelogram plus something times the second parallelogram plus something times the third one. So I'm just going to write it in this way and I'll explain something about it in a moment. So. So okay, so what's happening here is that again, this is supposed to be a linear combination of these three unit parallelograms. And you can call the coefficients anything you want in the world. You could call them C1, C2, C3, like, they could be called whatever you want. Uh, it's just that to make the connection more clear with the divergence that you know from Calc 3, it is better to kind of like use an index, right? To call the coefficients in terms of the kind of like the index that's missing. So for example, here you have three directions which are 1, 2, and 3, or E1, E2, E3. So for the one that involves E1, wedge E2, the number that's missing is 3. So that's why I'm calling this coefficient B3. For E2, wedge E3, the number that's missing is 1. So that's why I call this coefficient B1. For E3, wedge E1, the number that's missing is 2, so I'll call this coefficient B2. But again, that's completely arbitrary. I could have called the coefficients A, B, and C, or whatever letters. It's just that this one makes the connection a little bit more clear with the divergence. That's what I want to show you in a moment. Um, okay, and so each derivative, the way to define the derivative, let me see if I can write it here. Oh, actually, like, let's see, should I put this here? Oh, yeah. One way to write this. Well, let's just leave it like that. So the way to, okay. And then what is this derivative? Let me put this copy pasted on the next page. So the way that the derivative is defined for this is just as before. You just take the derivative of each of the coefficients, and then you wedge it with whatever was left. So wedge E1, E2 plus the derivative of the second coefficient, wedge E2, E3 plus the derivative of the of the last coefficient, let's just say last coefficient, wedge E3, E1. So the formula, that what I want to kind of like emphasize, that's why I'm kind of like doing this from scratch, is to show that the formula is always the same format. You just take the derivative of each coefficient, and then you just wedge it with whatever you had left. So it's, which is, if you look at, maybe just to go back for a second to the formula from like a week and a half ago, that is essentially what I was doing here with the curl, right? I had a vector field, and I define its derivative just by taking the derivative of each of the coefficients, wedge the thing that was left. Okay, so it's always, regardless of what you're working with, the exterior derivative, which is how it's called, is always the same format. It's always the derivative of the coefficient, wedge the rest. So it is very easy to remember because there's nothing really to think about if you just compute it that way. But now here's where the miracle happens, which is like the fun part. So if you, what is this going to be? It's one of those calculations that you kind of like do once in your life. So again, like the derivative of a coefficient is kind of like the derivative of the function. So it's kind of like a gradient. So it's like the derivative of B3 with respect to X, E1 plus the derivative of B3 with respect to Y, E2 plus the derivative of B3 with respect to Z, wedge, sorry, E3, and all of that is being wedged with E1, E2, and then you do the same for the other two. So again, this is kind of like the gradient, or so it's the derivative of B1 with respect to X, E1, plus the derivative of B1 with respect to Y, E2, plus the derivative of B1 with respect to Z E3 wedge E2 E3 plus the derivative of B2 with respect to X E1 plus the derivative of B2. Oh my God, this like app sometimes goes crazy with the lines. Okay. The derivative of B2 with respect to X E1 plus the derivative of B2 with respect to Y E2 plus the derivative of B2 with respect to Z E3 wedge E2 wedge E3. Sorry, like E3 wedge E1. Oops. Take it back. The purple one. Okay. But now comes like the massacre as before because if you look at them, so what happens here? If you do these, you have to distribute, right? So you would do like for example, the first one would be E1 wedge E1 wedge E2, right? So you would have two E1s, and that automatically goes away. If you do the second one with this one, you get E2 wedge E1 wedge E2. So now you have two E2s, so that one goes away. So the only one that survives is B3 with respect to Z, because that's the only one that gives you three different ones. So that gives you E3 wedge E1 wedge E2. Okay. Okay. Now, how about the next one? So again, the next one is kind of like similar. Let me start with this one. If you do the one in the middle with the blue one, right now you have two E2s, right? And that dies. So the moment you have two of the same vector, everything dies. Kind of like with the cross product is the same. Then two E3s here that would also kill it. So the only one that survives is the first one because that's the one that gives you E1 wedge E2 wedge E3. So here you have. And the last one, what happens with the last one? So this one dies because you would have two E1s, and then this one dies because then you would have two E3s when you wedge them all together. So only the one in the middle survives, right? Is that okay? And now this it starts to look awfully familiar, but it's not quite there yet because we just have to factorize some things out, right? Um, But every of all of these has like E3 wedge they all have like E3, E1, and E2 is just like in different order. So you just have to kind of like move terms around to kind of like so that it kind of like you can factor them together. So let me just do that to show you how it works. So and then kind of like something very fun happens. So for example, I'll just go slowly. So like you can like for example, if you swap these you can swap these two factors, but the price for swapping is that you get a minus sign. So you would put minus, and then you swap these two. So E1 wedge E3. So E1 wedge E3. Okay. I'll leave this one like as it is because this one is already numerically ordered, E1, E2, E3. And then here, what I'll do is kind of like, I'll swap these two together. So when you swap these two together, you get E1 wedge E3, but you have to put a minus sign. So again, whenever you swap, the price for swapping is to put a minus sign. So this would be E1 wedge E3. Okay. And then I'll do a final swapping of some of these, right? So now what I'll do is swap these two together. When you swap these two together, you get another minus sign that cancels this minus sign. So you get, again, for the one in the middle, I was never swapping, so I'll just leave it as it is. And for the next one, I'll swap these two together. And when you swap these two together, again, you get another minus sign that cancels out the minus sign that we had already. So you put a plus one more time. Okay, so this is, and now you have E1, wedge E2, wedge E3, E1, wedge E2, wedge E3, E1, wedge E2, wedge E3. So you can factor one of them as a single term. Right? Huh. But this is just a sum of partial derivatives, right? Like this is, if you organize them numerically, right? That's the derivative of B1 with respect to X plus the derivative of B2 with respect to Y plus the derivative of B3 with respect to Z, right? But that is literally, what would have been the gradient of a vector field, right? This thing in front of E1, wedge E2, wedge E3 coincides with sorry, not the gradient, the divergence. Oh my God, sorry about that. This coincides, right? If you had you defined a vector field which had been like B1, comma, B2, comma, B3, right? Its divergence would have been, if you remember from Calc 3, the divergence is kind of like this dot product thingy, right? And that coincides exactly with what you have there, right? Which would have been this. So essentially, my kind of like the takeaway of what I'm trying to say is that when you had a function, if you have a function, its derivative is kind of like the gradient. If you had a vector, its exterior derivative is more or less like the curl. Again, curl in quotes because it's no longer a vector, but it comes as a bivector. And if you have been given a bivector field, then its derivative is kind of like the divergence. So all these operations from calculus, like the gradient, the curl, the divergence, they really all have like a single formula that produces them all. And they look very similar, they're very different when you're learning them in Calc 3, like they look very distinct from one another. But they all kind of like can be kind of like, there's like a machine that produces all of them in exactly the same way every single time, which is just, you just take the derivative of each of the coefficients and wedge it with whatever else you had, and that produces all these like different cases of the formulas. So all of like Calc 3 is kind of like summarized, like just using this like exterior derivative business, which is kind of like very elegant and you know very, very cool. Like, so for example, just to, before I move to, you know, how to generalize this in, in the case of the simplicial complex, let's see, what should I put here? Should I write it down? Well, maybe I'll just it would take too much, but I'll put it here so that you see it, like Maxwell's equations, differential forms. Yeah, like I'll just show you that from Wikipedia to make it a bit easier. Right, so when you take like Maxwell's four equations, that's kind of like the typical vector calculus formulation. That's what you would call those. Um, what you can do using this technology of like the wedge product and the differential forms. And let's see, they probably have it here at some point. Like, let me see if I can scroll down a little bit more. Doo, 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 doo. Mhm. Yes, here you are. Right. So essentially what you do is that you can define something that's called the electromagnetic tensor, which it kind of combines the electric field and the magnetic field into a single entity. That's what like the theory of special relativity does, basically. And then all of the Maxwell's equations are basically just summarized by saying that the derivative of that thing is zero. And that's it. Like, oh, that's like all the four equations. Well, I mean, there are two because in vacuum, I mean, this is when there's no vacuum present. But it is really elegant because all the equations kind of like get summarized in a much more simple way. This is just saying that there's like a magnetic and electric potential under certain circumstances. Well, actually, it says here with topological restrictions. Actually, as it does depend on the topology of the space. But it is like very like very nice that you can have them like that. And there's like then there's the generalizations of Maxwell's equations, which you may have heard of, like which are called the Yang-Mills equations. So those are the ones that govern the standard model of particle physics, which standard model of particle physics are like the quarks, the leptons, the gluons, all the things that are like all the basic constituents of matter. So like, if you ever go to CERN or like all these like particle accelerators, like the equations for those are like called like the Yang-Mills equations, and they're basically kind of like a generalization of Maxwell's equations, but they kind of have like a very similar format. If you write them using this thing about the wedge product, they do look very similar to how the Maxwell's equations are written now. So it is like a very convenient like formulation of many things that you have seen, and as I kind of what we will do in the for the for like maybe the end of this week and the next one is, oh, how do you do like a version of the curl and the divergence and all this stuff on a simplicial complex, taking advantage of this formulation and apply it to these problems about the statistical ranking and this game theory stuff that I was mentioning, which again they're kind of like unexpected application. That's what kind of what I like about those. Also like some like problems in economics about currency exchanges. It can be used. You can use like the curl and all this stuff to understand them. So it's like a fun application of those things. So let me just maybe get started with that. See what I can tell you for today. I'll start with the grading because the grading is the easiest one to understand. And then next time I'll tell you a little bit of how you should define the curl and how you should find the divergence. Okay. But again, so by the way, before I forget, like remember that from Calc 3, um, you had these key identities or key equations, which were So there are different ways to write it, but one way to write them is that the curl of the gradient equals the zero vector, right? Which they would also write as the curl of grad of f equals zero. So these are like two ways to write them. And the other key equation that this one definitely you may have seen, although to be fair, like all that material is covered so quickly at the end of Calc 3 that you cannot really go into too many details about it. But this is kind of like a very important identity in Calc 3. That's why, as I had told you before, this is what you would have, you would, if you wanted to know if a vector field was conservative or not, you would check whether its curl would vanish. And that was related in particular to this identity. Um, and then the other key identity in Calc 3 is that the divergence of the curl of a vector is also vanishes, which you would write this way. Um, the idea is that, like again, in our versions with these exterior derivatives, basically this is just saying in the d of f equals zero. That's kind of like because everything becomes d. That's kind of like the fun part. Like there's only one single operation, which is called this exterior derivative. So you would get the d of df is zero, and the d of df is zero. Um, and that is why you kind of like summarize those two things as saying that d square equals zero. So that's kind of like the way you would say that, meaning that if you apply this operation twice, whatever you get always vanishes. Um, and that will be useful because in a moment when we start talking about how to define this on a simplicial complex, because what you do want is that when you give the definition on the simplicial complex or what the curl, the divergence, and the gradient should be, is that it should still have this property. So we want kind of like discrete versions of these things, but which still satisfy these key equations. That's kind of like what the idea is. So the goal is that to define a version of the gradient, the curl, and the divergence on a simplicial complex, which still satisfy these key equations. Okay, that is what we're aiming for. And again, just to kind of like draw some pictures of what a simplicial complex was like, right? Like a simplicial complex, just to have like a very simple picture of what we had as a simplicial complex, an example of a simplicial complex was something like this, where maybe you had three vertices, which I'll call V0, V1, V2, and a fourth vertex, which I'll call V3. And then you have these edges between the vertices, and one of these gets filled in with a triangle. Okay. So like, as a picture, that's what the simplicial complex would correspond to. Combinatorially, right? If you wanted to describe the simplicial complex combinatorially, you would, kind of like stage zero, you had the vertices, right? Which are kind of like, again, zero dimensional. The one-dimensional stuff would be the edges, right? Which you can label in terms of the endpoints of the edges. That's an important thing that we'll use in a moment. right? So in this case, how many edges do we have? We have 5 edges, right? So you could label these edges in terms of the endpoints. And then there's only one two-dimensional thing, which is the triangle. So this would be V0, V1, V2. Okay. So that's kind of like a simplicial complex in our case. Um, Okay, so let's start with the beginning. So if you have a scalar function, right? Let's say you have a scalar function on a simplicial complex. So how am I going to understand that? I'm going to understand that just as a function of the vertices. Okay, so again, like just to kind of like draw the analogy in Calc 3, right? Like just to go back to Calc 3, you have a function which would depend on f on x, y, and z, right? On a simplicial complex, that will be replaced with the function that's defined. Again, like this function is defined on the points in space, right? Kind of like the analog of the points in space on a simplicial complex are the vertices. So what our function will be is a function defined on the vertex set. Okay, so in this case, on the simplicial complex, the function is a function of v, where v is like a vertex, right? So here v is a vertex. So a function for us on a simplicial complex would be a function from the vertex set to the real numbers, right? So it's a function from the vertex to the real numbers. So a function assigns a number, which I talked about that a little bit when I said that, when you had the Laplacian matrix that you can kind of like do a, kind of like a Fourier series type decomposition for these things. But the idea is that, I'm sorry, I'm trying to, right. The idea is that the, the function kind of like has to assign a value to each vertex. So you can represent that kind of like as a tower, if you want to think about this as some sort of like signal analysis where like you have at each, if you think of each vertex as being where like a sensor is positioned or something like that, then the value of the function at that sensor, would be related to the strength of the signal or something of that sort. So like pictorially, it's just like a bunch of numbers that you give to each vertex. That's what a function is for our purpose. Okay, a collection of numbers, which again, you can also think about this as a vector, right? So it would also be the vector f of v0, f of v1, f of v2, and f of v3. Uh, so that is what the function is. And again, in Calc 3, the gradient would have been a vector field, right? So we already know the definition of the gradient in Calc 3, right? The gradient of f, that would be a vector field, right? So it is a vector at each point, right? So it's a vector at each point. Right now, the idea is that if I have a function defined on the vertex set, right, I want to define the gradient of that function now. Actually, maybe I'll use the Calc 3 notation for like the continuous version, and I'll use like the language version for like the discrete version. So if you have a simplicial complex, You want to define grad of f, but now f is a function defined on the vertices, right? So these, you want it to be a vector field of sorts, right? But then, so you want the output to be a vector or a vector field. So, okay. But then you have to think, okay, what is what is a vector? Again, a vector is somehow something one-dimensional, right? That is what a vector is. And then on a simplicial complex, right? Uh, on a simplicial complex, the data that's kind of like one-dimensional in a simplicial complex are the edges, right? So somehow these should be related to the edges of the simplicial complex, okay, what it spits out. But as I was saying a bit earlier, to specify the edges in a simplicial complex is kind of like, you might as well just give me the endpoints of the, sorry, like the endpoints of the edges, kind of like the initial point and the final point of each edge. So kind of one way to think about a vector on a simplicial complex is in terms of two vertices, because the moment that you have two vertices, provided that that edge is on the simplicial complex, that would give you a vector. So the idea is that you define, okay? So the idea is that the key idea is that to think is that a vector is one-dimensional in a sense, one-dimensional in some sense, and on a simplicial complex, the edges are one-dimensional. Okay? And the edges can be specified, and the edges can be specified in terms, or let me put it like this, each edge can be specified in terms of the of two vertices, right? Like the, okay. So basically what I'm going to do is say what the gradient should be at each edge, okay? And then I'll draw a picture so that you see, So in this notation, okay, I'm going to say like I'll draw a picture. Maybe let me draw a picture now. So I have an edge. Think of an edge as having point vector. It goes from a vertex v to a vertex v prime. Okay, and at each vertex you have a value for the function f of v and f of v prime. Okay. And so, like the gradient is supposed to be a derivative, right? So the gradient is supposed to be a derivative. Of course, you cannot take a derivative on a simplicial complex because lengths do not make sense, right? So because remember, like the simplicial complexes are abstract. So if you think about it in the case of the social networks with friendships, right? Like we were drawing an edge whenever two people were friends, that has nothing to do with distances, right? Like it's just kind of like a pictorial way to think about it, right? But it's not that it's not that you can take a limit as h goes to 0 or something like that. That doesn't make sense because again, these edges really, whether you draw them super long or super short, it doesn't matter for the complex. It only matters that there is an edge, right? Like the size is kind of like immaterial. So kind of like But you can still think of a derivative as kind of like being delta f over delta x, but the delta x part has no meaning, so you just keep the delta f part, and so it's kind of like a difference in the values of the function. That is kind of like the closest to a derivative that you could ask if you have no good size of length on the complex. So you kind of like define the derivative to be just like the comparison of the function at the endpoints. That is the best we can do. So it kind of like just gets defined as f of b prime minus f of b. So that is the formula for what the gradient is at each edge, essentially. So for example, what I'm trying to say, maybe this is not complete formula. Like, this is a correct one, provided that, let me put it like this. And this is true, but really, it is, if like this is like the formula, if there is an edge that connects the two vertices, that's how you should think about this. So if v prime are connected by an edge, and if they're not connected by an edge, just for to make your life easier, you can just define that to be zero. So and then you set it up equal to zero if v prime are not connected by an edge. So for example, maybe I'll just do this to finish for today. Because the curl does take a little bit more time, but it's kind of like the more interesting definition, how to define the curl. But like the gradient is, I mean, not too hard to convince yourself that that's kind of like a reasonable thing to do. But if you had like imagine that your complex had just been like, you know, if it had just been like, um, three vertices, right? And they just make up, and then two of these vertices are connected. Okay. But the first one and the last one are not connected. So it's just, you know, something like this. And your function, let's say that your function assigns, I'll again, just to draw it pictorially, let's say it assigns the value two, it assigns the value two to the vertex zero, right? It assigns the value five to the vertex one, and it assigns the value three to the vertex two. Or to the last vertex, the vertex v0. So meaning that the function is f of v0 equals 2, f of v1 equals 5, and f of v2 equals 3. By the way, like which is where we're headed with as an application. I can say this one it kind of like would work. If you thought about this as a ranking, right? This could be the ranking that a user gives to three movies, right? So like in terms of stars, or like like Rotten Tomatoes. I guess well that one is kind of like more a percentage. I don't know if it's like big. But Netflix, it's like 1 to 5 stars, right? So you could be, I mean, if you wanted to, you could be like, oh, this is kind of like the number of stars like the user gave to a particular movie. Of course, we'll do something a bit more interesting than that, but I'm just saying like that is one way to think about this. Okay, and so the gradient, right? The gradient of this function, the way to think about the gradient is that it kind of like records all the possible differences in the values of the function at the different vertices. So you have to say, you basically, okay, well, I mean, we're not defining it when the vertices are repeated. So 2 times 3 is 6, right? So there are 6 possibilities that you could have done this for. So, grad of f. So it is in a sense kind of like a pairwise. Actually, let me put it like this. Because again, in Calc 3, like the gradient is a vector field, so there is a vector at each point. Here, kind of like the idea is kind of like there is kind of like a gradient. The gradient, if you want it to be a vector, kind of like a vector of sorts, would be in terms of the edges, and the edges are in terms of the vertices. So you kind of like evaluate the gradient at pairs of vertices. So you would evaluate it at, it would get evaluated at V0 with V2 or V0, sorry, V0 with V1. Let's start with that one. V0 with V1, V0 with V2, V1 with V2, right? And then in the opposite order, which would be V1 with V0, V2 with V0, and V2 with V1. And it's kind of like a difference in the values, kind of like of the, if you think of this as ordered pairs, it does f of v1 minus f of v0, right? So this would be 5 minus 2, right? And the other one just goes the other way. So the other one is just 2 minus 5. And then the next one is v2 minus, there you just assign it to 0 because these are not connected by an edge. So that's the easiest way. And then the other one, it's 2 minus V2 minus V1. So it's 3 minus 5, right? And then 5 minus 3. Okay. And the reason for doing it that way, if you wanted to, which is a useful representation, as you can imagine, as matrices, if you thought about this as along the Venn diagonal, like you always get zeros like almost by default, and you can set them equal to 0 because it's just like and then well, I mean, you just have to then you just choose your convention of how you're labeling this, but you can do it this way. V0, V2, which is 0. The point is that like if you want to like you could represent all these differences in values of the function in terms of a matrix, and the way the gradient is being defined is so that by default it always ends up being skew symmetric. So a skew symmetric matrix is one that equals its minus its transpose. So in this case, this representation for the matrix for the gradient. So if you think, oops, sorry about that. So if you call this like kind of like the gradient matrix as a matrix, it satisfies that its transpose is minus the matrix. And those matrices in linear algebra are called skew symmetric. And if you remember, I mean, that's not too hard to show in linear algebra that, if you have a skew symmetric matrix, the diagonal entries are always 0. The thing that will happen with the curl is that it kind of like, if you do it in this way, instead of being represented by a matrix, it kind of like gets represented by a box, which is called like a tensor, like a a cube, and it's kind of like fun. And I'll show you more about that next time. But not that, again, it's not like the same with the linear transformation. No one is twisting your arm into thinking about this. You're gonna always think about it more abstractly, where this like the gradient is just this device to compare the values of the function assigned at the different vertices. But more concretely, if you wanted to, once you choose the ordering of the vertices, labeling, then you can always represent it as a matrix, which happens to be skew symmetric. Right, but like the more abstract representation is kind of like the more elegant, which is just like a comparison of values. The gradient stores the information about the differences in the values of the of the function at the vertex. And that's actually how it would be more related to the ranking, which we'll start doing like next time, because the idea is that you can imagine that you have like users making pairwise comparisons between like say movies or like products, and then those pairwise comparisons can be stored kind of like in terms of like these edges, and then you can ask whether those pairwise comparisons can kind of like come from the gradient of a function. So that's kind of like asking whether a vector field is conservative or not. So it's kind of like the discrete version of calculus theory when you're asked, is a vector field conservative? And you would need, oh, is the curl vanishing or not? And so you kind of, that's how you start getting into all these questions about the curl and what have you. So it's kind of like a fun part, but we're almost out of time, and like it's better to start the curl fresh on Thursday. So we'll be doing that, and I'll give you some examples about how we want to use it, which are kind of like fun for like this economic stuff and the ranking problem.